Okay, so, well, if we're going to solve a linear system like this, let's start by writing out its augmented matrix. So the augmented matrix of this linear system, I'll just write the AM, just short for augmented matrix, is, well, what are we going to have? The first row is going to be 1, because the coefficient of C1 is 1, right? The coefficient of C2, well, there's no C2 in that equation, so we're going to have a 0, and then C3 has a coefficient of -1. So then that is going to be our first row with a 1 on the right-hand side. And we're just writing down an augmented matrix here, so I'll do the next 3 rows a little more quickly. So we're going to have 0, 1, 0, 4 for the second row, and then we'll have 1, 0, 0, 1, and then for the fourth row we'll have 0, 1, -1, and 3. So that is our augmented matrix. Well, let's just get it into reduced row echelon form and see if it has a solution. And the way this question was worded, you're expecting it not to have a solution, because what would it mean if we did have a solution? Well, that would mean that there is a choice of C1, C2, and C3 that makes this equation true, or equivalently makes this equation true. But if you can find values of C1, C2, and C3 that make this equation true, well, that means that this vector is a linear combination of these 3 vectors. But the whole point of this question is that we were asked to show the contrary, to show that this vector is not a linear combination of these 3 vectors. So for that reason, it's natural for us to expect that we're not going to get a solution for this. But let's just check carefully anyway. So what we can do is we'll take row 1 and subtract it from row 3. So how about we do that? So we'll take row 3 and replace it with row 3 minus row 1. So what we'll get, and then everything else we'll just leave as is. So then our first row won't change. We'll have 1, 0, minus 1, 1. Second row is still going to be 0, 1, 0, 4. Our third row is going to be, well, 1 minus 1 is 0. 0 minus 0 is 0. 0 minus -1 is +1. And then 1 minus 1 is 0. So last we'll get a 0 there for the fourth entry in that row. And then the fourth row won't change. We'll have 0, 1, -1, and 3. Okay, well, what's next? Now we're going to take row 4. If we're doing Gauss-Jordan elimination, this is what your next step would be. Take row 4 and subtract row 2, and that'll get rid of this 1. So we'll go row 4 minus row 2, and what's that going to give us? So the first 3 rows aren't going to change. We'll have 1, 0, -1, 1, 0, 1, 0, 4, 0, 0, 1, 0, and then what's going to happen here? Well, we subtract 1 minus 1, well, sorry, back it up. 0 minus 0 will just be 0. 1 minus 1, well, now it's going to be 0. And we have -1 minus 0. That's just going to be -1. And then lastly, 3 minus 4, that's going to be -1 as well. So we have -1 there. Okay, and then now, so our first 2 columns are great. That we're almost in reduced row echelon form. If we're going to get it into row echelon form next, then our next step would be to take row 3 and subtract it from row 4. And then afterwards, if we want, then we'll probably take row 3 and add it to row 1 afterwards to get rid of that -1. But let's just do one step at a time and take row 3 and subtract it from row 4. It actually turns out that that's going to be enough to finish the problem, as we'll see in a moment. So what happens if we do that? If we take row 4 and replace it with row 4 plus row 3, just to get rid of that -1 in that position there, well, what we're going to have, well, the first 3 rows won't change again. So 1, 0, -1, 1, 0, 1, 0, 4, 0, 0, 1, 0. So those are all going to be the same. And then the fourth row, 0 plus 0 and 0 plus 0, we're just going to have 0 for the first 2 entries. -1 plus +1 is going to be 0. And then -1 plus 0 is going to be -1. Now this is not yet in reduced row echelon form, but it is in row echelon form, and something should stand out at this point, because what the fourth row is a contradictory row. So this is a contradictory row. This is the fun part. Let's take our time and identify this carefully. This is contradictory row. So really what that tells you, if we go back up to this linear system, it means that this linear system has no solution. So in other words, there are no values C1, C2, and C3 that make this linear system be satisfied, or equivalently make this equation true, or again, more importantly, make this original equation true. So that violates this assumption, because we started off by assuming we had it in mind that we were going to get a contradiction, but this is the contradiction. We supposed that this is possible. We supposed that there was some values C1, C2, and C3 that would make this equation true, but it turns out that's contradicted by the existence of this row. So this is a contradiction. Let's finish this off completely informally. So we say this is a contradiction, and therefore this vector that we started with, so I'll just summarize what we had, 1, 4, 1, 3, is not a linear combination of those other three vectors, which were, let's just finish it off to be complete, 1, 0, 1, 0, 0, 1, 0, 1, and then finally negative 1, 0, 0, negative 1. Okay, so that is our conclusion. Let's highlight that as our final answer, because that's obviously the work is important, but our conclusion is very important. So we want to make that clearly stand out to the reader. So that is how you can solve problems like this. And remember, I mentioned this at the beginning, but I want to remind you, if this had been worded differently, because you will see exercises like this where you're asked to show that a vector is a linear combination of a handful of other vectors. You're going to start out in this exact same way. You're going to start out by writing out something like this, write it out as if it were a linear combination, and try to find out what the scalars would have to be. And you're going to do that by collapsing the right-hand side of the equation, which is going to give you something like this, and that's how you're going to get your linear system. And solving that linear system is going to tell you what your options are for these scalars. Okay, so that is the end of section 3.1.